All right, very good. Thank you. Microphone working okay? Excellent. All right, so it's a pleasure to be here. Morning was full of inspirational talks, and I really want to thank the organizers for including me and Zoox as part of this. And although I am a faculty member at MIT, I'm on leave. And what I'm going to be talking about today is a lot of the exciting work that's going on at Zoox. And I want to emphasize that I am representing, a bunch of people and a lot of different contributions here, some of whom are here because I've ruthlessly stolen slides from their own presentations. But there's many more people supporting this as well. I have the pleasure of helping lead the architecture group at Zoox. Yeah, there we go. And one of the things that I wanted to talk. All right, this works. Very good. One of the things that I want to talk about is Zoox's perspective on how to actually organize a lot of the processes that go into developing and operating an autonomous vehicle. Had I given this talk even 6 or 7 years ago, I think that I could have rendered this, or I know I could have rendered this architecture and said that pretty much every single operational autonomous robot of any kind, whether it is a vehicle on the streets, whether it is a rover exploring the surface of Mars, whether it's a factory robot, more or less is an architecture that looks like this, where we have sensor data that feeds into some kind of estimator that estimates the position, whether it's using GPS or doing entirely onboard exteroceptive sensing. That produces typically some kind of probabilistic estimate that then goes into a planning system. If you're operating in a dynamic environment like a self-driving car does, then you might have a prediction system, and that goes into a controller. And that bottom layer of computation is replicated in almost every system that exists, or certainly every system that existed at the time, and worked extremely well. We have been very good as a community at deploying robots that can move around through the world more or less collision-free for a long time. But that bottom layer is really only good for doing one thing, which is actually moving through what we typically think of as configuration space, moving from point A to point B. So if you actually want to do any kind of complicated mission, such as picking up passengers and dropping them off at a location, whether you're a drone doing deliveries in the environment, you typically have some kind of executive at the top that's sequencing the goals that you have to get to from point to point. And so we typically see 2 layers of computation, maybe 3 sometimes, that operate at different duty cycles. And that's really important when we think about the architecture of our systems. Now, I said if I'd given this talk like 5 or 6 years ago, pretty much every single system that we had operated that way. Things have changed a lot in the last few years. And now we have architectures that look a lot more like this, where we have like a learned controller that in many cases are going directly from the raw sensor input straight to the motors. And it's worth noting that even if you have a learned system that's doing a lot of the actual motion through the system, motion through the world, you typically have to have some kind of symbolic representation of the goals, if nothing else, to tell the humans that are in the loop somewhere. There's always a human in the loop somewhere. What exactly it is that you're trying to do and why, and maybe allowing the human to inject some additional guidance. It's also worth noting that these 2 architectures really represent 2 points on a continuum of possible architectures. On the left, I have the first architecture that I drew. It's often referred to in the literature as a classical architecture. I don't really like that designation. It suggests sort of like that architecture was devised by Gauss and Bayes themselves in a series of letters that were passed between Göttingen and Kent 300 years ago. It's still actually far and away the dominant architecture that's used by operational robots around the world. And then, of course, we have sort of what are typically referred to as end-to-end learned policies at the other end. And it's worth also thinking about what are the relative advantages and disadvantages of these architectures. The structured optimization architecture, the first one I described, is usually interpretable. Usually it's written, that's architected by people, and they put a lot of domain knowledge in there so that we can actually get a sense of agents as agents around our robot and objects as objects, et cetera. It brings with it a lot of the time an increased ability to provide guarantees. That's not to say the guarantees are easy, and sometimes they're not even available. But a lot of the technologies that we have for providing formal guarantees and verifying our systems are more available on the left. Joshua Bengio has been on the record saying publicly he thinks that guarantees of learned policies will only ever be available statistically. On the other hand, Drew Bagnell has taken the position that statistical guarantees are the only thing that matter anyhow, and he himself would never not get on an airplane that had only been formally guaranteed and never been flown. and he's not entirely without reason. It's probably the case that the left architecture is more data efficient. Certainly, VC dimension of a lot of the models on the left are smaller. And so, many verify or getting the data, learning the models of a smaller VC dimension is typically much easier than one big model of a much higher VC complexity. On the other hand, the left thing, structured optimization. Optimization is a very computationally expensive process, and it's usually more expensive on the left. On the other hand, we certainly believe that learned architectures are showing themselves to be more flexible. They're showing them to be more computationally efficient because you get to amortize a lot of the very expensive computation offboard over the lifetime of the vehicle. We typically don't have to write more code to generalize to more instances. On the other hand, I think most of us understand the amount of data required to do learning for any system of reasonable complexity. Some of the speakers this morning were articulating that that's really only increasingly available. I think Bolay was the one who said it's really only available in industry, and academia doesn't have the ability to scale. I'm not sure that I completely agree with that, but certainly it's the case that the architecture on the right is more data intensive. So the question then is, how do we get the best of both worlds? And many of you may be putting yourselves at different places on the continuum, and almost nobody's really all the way on the left. And there's not that many people who are deploying full end-to-end learned systems on self-driving cars on the right. Some of them may be in this room. I don't want to make judgment calls, but most of us live on the continuum somewhere. And Zoox is no exception. And the position that Zoox is taking at the moment is really trying to, and we're not the only ones, and I don't want to pretend we're the only ones, where there's tremendous value in learning a representation of the world and where we are in it, but not actually learning all the way to the end, that actually creating a learned representation that is also interpretable and then is fed to that symbolic state executive at the top is really useful for a lot of the reasons that I said. We get a lot of the benefit out of learning in terms of flexibility and computational efficiency, but we get a lot of the benefit in terms of verification, interpretability that's available. And we're not going to pretend that we don't have a symbolic state executive that allows us to specify goals for picking up, dropping off, fleet management, et cetera. So most of what I'm going to talk today about is some of the challenges that we have faced in developing this particular architecture, and 3 of them are here. And I'm mostly, but not exclusively, going to talk about our learned estimation scheme. I mean, this is, after all, CVPR. And so what are the issues in terms of having a learned estimation that fits in the overall architecture for the system? So the first one that I want to talk about is that we really, if we're going to have a learned system that's outputting a particular representation, we actually have to make design decisions around the representation. One of the advantages of a full end-to-end learning system is that it's going to pick the representation itself. There's an entire conference called ICLR, the Conference for Learned Representations. We're actually going to make design decisions about the representation, recognizing the reality that that representation is we're going to want it to be interpretable, and we're going to want to feed it into a mission planner at the top there. And so we want that representation to be designed for the entire system. So one of the things that's true about the Zoox vehicle is that we have a lot of sensors. We have more than most of our fellow, as Aisha, our CEO, likes to call them, fellow travelers in the journey to full self-driving. And so the question is, how do we actually process that sensor data? And one of the things that we are moving to, and many of you are ahead of us in that regard, but we are doing so at our own pace, is that we are not taking the position that we're going to process each of those sensor streams separately, but we're actually going to process those sensor streams together. So we're actually going to, what is now being increasingly called early fusion, combining our cameras, our LiDARs, and our radars into a single representation of the world. And so we're committing to a unified representation that combines the radars, all the LiDARs and cameras, et cetera. And this brings with it, without a doubt, data challenges and computational challenges, but it gives us the ability to reason about the world in some interesting ways. So one of the ways that it gives is that we don't actually have to commit to a particular representation that's human interpretable out of the sensors immediately. We're going to delay the decision to commit to that particular representation. So we've actually done a complete inference over all of the scene, geometry and velocity, et cetera. So this particular video here is some of our most recent results in building a representation that captures higher order attributes such as velocity before we actually commit to the notion of other agents. And what that means is that we don't have to perform things like agent detection, car detection, vehicle detection before we can actually do inference over the velocity of components of the scene. We can for instance, infer the existence of objects who we can't even necessarily recognize as, say the proverbial dumpster rolling down the hill at us. Before we detect that something's moving in the environment, we need to do something about it. We still have the ability to extract the notion of agents with a particular velocity, and that's present in the image down in the bottom left. But we're able to extract the velocity, and that's really important for recognizing the world is full of things that we might not necessarily know about ahead of time, and we need to know that they're moving in order to plan robustly around them. And we're not the only entity, organization that has a representation of the world. Lots of other of you in this room may, in fact, we have representations, but we're really committing to this idea of a full representation of the scene that's fusing all of the attributes of the different sensors in one unified representation before we start extracting the semantically relevant bits that are really meant to feed into that higher level symbolic planning system. Another ability that this fusion gives us is the ability, for instance, to complete parts of the scene that may not be directly observable. So something that learning doesn't necessarily do a great job of is reasoning probabilistically a lot of the time, and I'll talk more about that in a minute. But probability and theory in particular gives us the ability to reason about things like observability. So if you are a classical control theorist, the notion of observability is really familiar to you in that it's it's what happens when the observability matrix is no longer full rank. Well, learned systems don't have the notion of observability. They don't have the notion of an observability matrix, in fact. And so the question is, what do you do when you actually can't necessarily observe all attributes as seen in any particular sensor stream? I don't have an answer to that necessarily, but one of the things that we can do is we can leverage, learn models and previous data to complete parts of the scene that are not necessarily directly observable to us. And so this is some of the work that Nick Green in particular has done in terms of actually using, past data from different sensors in order to actually learn to complete the depth model for us. And again, we're completing a human interpretable depth model, in this case, the road surface, in order to be able to make planning decisions. The notion of learned depth completion has been around for a really long time. In fact, it was present in the first DARPA Grand Challenge many years ago. But fusing the notion of depth completion across multiple sensors is something that we've only seen certainly in the literature and that we've been able to do in the last few years. But the idea of a system wide representation shows itself, I think, most acutely in the notion of debris. So debris is something that we have, and I suspect many of you have also wrestled with in recent years. The idea that there might be objects in the world that we don't know anything about. And many of them are often hard to see. So the notion of a wooden plank in the road or a flat tarp. And the question is, do you drive over it or not? Do you even recognize it? How do you put it into the world representation? And debris that we experience in the world on the road surface, where we don't necessarily know what it is particularly hard to detect from a single modality alone. Debris from a vision perspective, has a high variability in appearance. There are a lot of the time there are false positives, and then there may be like patterns on the road that we don't necessarily know about. And detection is fundamental in camera images is fundamentally, at least initially, a 2D process. Contrast that with LiDAR, where the debris is often characterized by having very sparse points. We can't get much in the way of texture. These are two examples that we've encountered where the debris in particular is very, very hard to see in both the LiDAR data and the camera data. And without getting into the details of how we actually detect debris, the point for us is that we really recognize that there's a whole class of objects out there that are, we're all familiar with the long tail, that we're never going to be able to get any particular kind of classification. The idea of actually training a classifier around debris is not a sane concept. But what is a sane concept is, are there properties of the scene that have implications for planning? The real issue for debris is, do you drive over it or not? Is it dangerous or not? What is the level of risk? And so this particular video here shows the results of our debris classifier, where we haven't trained a system to actually recognize debris or not debris. What we have trained is, what is the level of risk for our planner? And we're using a planner that computes expected costs. And so we can actually train a classifier here, really a regression model, to actually predict discrete levels of cost, and then incorporate that into the planning system. So this, I think, is a really, really good example of why we at Zoox in particular have chosen a particular architecture that outputs interpretable representations that have system-wide implications. Is that debris itself is not really interpretable from a human being, but it is interpretable by a planner in terms of what is the expected cost. And we're familiar as human drivers with the notion of avoiding debris by when we can, but also taking some risk and driving over things like a plastic bag when avoiding it might, especially at high speed, might bring risks of its own. And we can do a more principled trade-off in terms of those kinds of costs. Okay, so one of the principles that we're pursuing in this particular architecture is the idea that we can design representations explicitly that are intended to support human interpretability, and we can design representations that are designed to support the needs of the planner, but at the same time, we can train the learner to meet those particular requirements. But I think a common theme, looking back at a lot of the presentations at this workshop and over, so I think this is the 7th iteration of this particular workshop, a common theme over many years has been, what do we do about learned systems in the real world where we're going to encounter sensor data, we're going to encounter concepts that we haven't seen before. Machine learning has this very brittle assumption that we're familiar with. All our learning algorithms assume that all the data are independent and identically distributed. And that's just not true of embodied intelligence, agents acting in the real world. We're going to encounter scenes, images that are outside the support of our training data. And what do we do about them? And so we also have some things to say about this. OOD detection has been well studied in the literature for many years. These examples here were pulled up by somebody that we had working on this. I wish I could say we actually encountered these in the real world. We haven't encountered anything necessarily as exciting as this, but it's not hard to believe that driving through the streets of San Francisco or Seattle, you might see something like this. So what is known about saying something about how much you can trust your learner when it's presented with an image like this that it hasn't been trained on? Well, a lot of work has been done on this problem. There's a few representative citations on the right here. I know some of the authors in this room are in this room. If you haven't seen the particular survey by Galakowski and about 30 other people, I highly recommend it. It's very, very thorough for actually understanding how to model the uncertainty out of especially deep learned models. But it's not hard to get a learned model to output its own output distribution, which is in essence is a distribution over possible errors. One of the problems with trusting the output of a learned model is that it tends to conflate things like a label uncertainty or loss of observability with uncertainty that might come from the fact this is an unfamiliar training instance. And so, experience indicates, not just from us, but from a lot of the literature, is that simply training a deep network to be uncertain about its own model is not necessarily the best way you can go about doing out-of-distribution detection. Another approach is to actually look at the input density, try and model the density of the training data, and to notice when a particular query is far from the training distribution. And you can build a model of the input density using something that the most common technique in the literature is this idea of a normalizing flow. So one of the problems with deep networks is they're building their own internal representations. They're building their own features. And we train our neural networks to use all of the available computation to express the training data. There's no input feature representation. There's no computational power that's spent on anything other than representing the input data for the purposes of the loss function. And so what that means is that when you have a query that's far from the training data, it's going to be far from the features that you train the neural network. And so you can get a problem of aliasing where your novel query can actually look very, very, very similar in feature space to your training data. And the neural network has no way of knowing whether or not it's really far. So one of the normalizing flows basically forces a probability distribution to have representational power. I mean, I'm blurring over a whole pile of details, but a normalizing flow basically forces the density estimation to have representational power everywhere. It's going to try and put as little representational power over places that are far from the training data, but it's going to put some. And so this kind of basically hedges against against the aliasing problem. But one of the problems with normalizing flows is that they are very computationally expensive. You're basically forced to have an entire other network for representing the training, the input density separate from the task at hand. And so you're still a little bit vulnerable to aliasing without normalizing flow, and it's computationally heavy. One of the things we've been able to take advantage of is the recent work in foundation models. So the essence of a foundation model, and more accurately, the essence of the pre-training process, is to try and make sure that you have a representation that's going to generalize against all the things that you can think that you might ask your network to encounter. So that's really what pre-training is doing. It's trying to build that representation that like sees all the things and knows all the things. And so aliasing is much less of a concern now. And so one of the things we thought was like, well, okay, if aliasing isn't a concern, maybe we don't have to have the full computational power of a normalizing flow network. And we can just build a density estimator over our latent space, our foundation model features, and then use that to predict whether or not the query instance is low probability and do something about that. And so we tried this on a few of your favorite foundation models, and we actually got fairly good performance. So in this case, positive means it's in distribution. So false positive means we got a query from a held out training set that we thought would be out of distribution, that the network thought was in distribution. And you can see we tried a few different foundation models. We got pretty good performance on using Dyno v2. So that was very encouraging. Mind you, we actually had a task at hand. So we picked a task that we do on vehicle, which is to actually classify vehicle lights. And the way that we typically use the vehicle light train the vehicle light classifier, is to take a foundation model and then do fine tuning, as we all do on the vehicle light classification task. Alas, the fine tuning basically destroyed all of the representational power that a foundation model had carefully built up. And all of a sudden we got very bad out of distribution detection. And in fact, our held out of distribution set in orange, all of a sudden looked incredibly in distribution on the vehicle light classification test. So that was sad for us. But happily, Till and Daniel had an excellent idea of actually regularizing against the original foundation feature. So do your fine tuning while actually telling your fine tuner to actually try and preserve a lot of that representational power of the foundation model. And huzzah, we all of a sudden got back a lot of our performance. You give up, there's no free lunch here. And so we gave up a little bit in terms of out of distribution detection performance, and we gave up a little bit of vehicle light classification performance, but not so much that it was a problematic. And so now our aligned features are aligned with the foundation model, do well at both of these tasks. And just to give you a flavor of some of the kinds of things that we can do with this is that, you could see that the things that are far from in distribution on the top left here, but we're still in distribution, are sort of odd things like, badly saturated vehicle lights or vehicles of the kind we hadn't seen before. But a lot of the things that were out of distribution are the trucks on the bottom left. And so we've got now a process in place for taking advantage of foundation models, and we're trying to now deploy that more widely in the different systems. And the really nice thing about this particular form of input density estimation on the foundation models is that we're using the same features that we were using for the task anyhow. So the computational hit that we're taking, that a lot of systems that do out of distribution detection are taking is de minimis here, very little computational overhead. So that's very nice for us. And so that's another reason why we have this architecture, is that we can do out of distribution detection in advance of making decisions. And so what that means is that we can tell the planner, we're very uncertain about what this particular entity is. And the planner, again, computing expected costs, can plan according to the fact that we don't really know exactly what this thing is that we're looking at. But at the end of the day, how am I doing on time here? Oh, I've got 7 minutes. All right. At the end of the day, we do need to train these models. And so we need some way to actually get the data. And so once again, this particular structure for us is very, very useful because it allows us to avoid having to pay, or let me back up a second. At the end of the day, data is very expensive, and we can go out and get it from the real world, but we can't really get all the data that we need. So we have to do simulation. There were a lot of great talks this morning about different ways to do simulation. But we don't really want to pay a lot of the computational costs that we saw this morning, that like doing end-to-end photorealistic simulation with all the physics and all of the closed loop driving is maybe a cost that we have decided that we don't necessarily want to incur. And so actually being able to simulate the output of the perception system without actually having to run the entire system and be able to simulate the interpretable symbolic representation is really powerful for us in being able to generate scenarios that allow us to test out, for instance, the planning system. So this is a little bit more about how we replicate the effects of the learned perception system without actually having to run the full learned perception system. So the problem that we really want here is that we have some description of a desired scenario, again, human interpretable, and we want to generate a scenario that we can run in simulation without actually having to do the full photorealistic simulation. We want to test out a closed loop simulation. And we're going to fill this, of course, with yet more AI magic. The thing that we're really going to use here is a diffusion model. And Bolay talked about some work that he and his group have done in diffusion modeling. We're definitely inspired by that, traffic gen for sure, and also scenario gen and others. But the thing for us that we really want is a lot of the existing diffusion work was conditioned on the world representation. And so you could, like, just for those who don't know, diffusion basically generates random noise and then as a learned model, it progressively refines it until you get the concept that you want. And so you can imagine generating like other agents around you somewhat at random, and then using the diffusion process to slowly refine that until you get to a scenario that actually has like agents in sane places in the map and going sane velocities, and then you can run your forward simulation around that. But this is conditioned on the map for sure. But we really wanted some way for the engineers or to either be able to give an example scenario and say, please simulate a bunch of things like this, or even better, be able to type a description of a scene and say, please simulate a bunch of things like this. And so our diffusion model is not just conditioned on the environment and the map that we want to condition on, but we're also able to condition on tokens that the engineers might give. And so here's an example where we condition on, say, two agents at a particular environment. So let's say agent A is us and agent B is, no, I think it's the other way around. Agent A is some other agent and agent B is us. And we can even say the extent to which we want to populate it at random with other agents that we might be interacting with or have to drive around. And we can go use our diffusion model to explicitly condition on that set of tokens. The most revolutionary idea, conditioned diffusion is something that's been around, but we're very pleased that we're able to use this to do our scenario generation. Essentially, our structured representation, our structured architecture gives us a way to simulate these things and then run simulation and validate a lot of the planning system that we're developing. And so we can condition on specific interactions that we might have between agents to test cases. So that's a U-turn. We can do things like parking or get on road, where, again, condition on, say, the parking token, we can put a particular agent in a particular location pulling out of a parking spot. We can also control the extent to which there are other agents that are parked in that scenario. And of course, it's a diffusion model, so we can control the extent to which we're fuzzing the scenarios and control the variation of the scenarios that we can produce in this case. And the really useful thing is that we can combine both an existing scenario that has existing agents in it. We can condition on that scenario and those agents and the natural language tokens as well. So it gives us a very seamless way to like inject both the results of the perception system for a particular log and the additional variations in the scenario that the engineer might be actually wanting to condition on. And so other folks have done things like adversarial generation of scenarios, looking for ones that are most difficult. This has given us the ability to actually inject domain knowledge and actually generate a wide variety of scenarios specific to the particular scenario that we're conditioning on. So I've talked a lot about these particular issues in the autonomy architecture. I do want to take last couple of minutes here and talk about Learn Planner. Well, I'm actually not going to talk about the Learn Planner. We do have some work on Learn Planning here, but rather than talk about it, I'm going to point you to a workshop tomorrow where Moritz is going to be talking about some work that we're doing in JAX-Accelerated reinforcement learning. So the idea, of course, is like we want to have use reinforcement learning to learn to drive not only like humans, but in fact better than humans. That is really hard to do, to outperform human behavior. I think a lot of the evidence is that human behavior is a really good training signal. If you want to go beyond that, then scaling up to the defense of the arts or AlphaStar, that requires an enormous amount of data. And gathering and in particular, you'd actually like the data to match a lot of the experience that you have. And so without getting into the details, and please go and talk to Morris tomorrow at the workshop about the work that we've done, is actually being able to show that we can scale up by taking advantage of computational and, basically, good engineering processes, figuring out how to perform parallel execution, being able to take advantage of JAX in order to actually, combine the simulator with the RL framework and be able to train policies with, very, very large amounts of data, much more than we're able to do before. The reality, unfortunately, is that the volume of data is still very, very computationally demanding. And the second speaker this morning, whose name I'm blanking on, I think it was Kalyak, really alluded to this, is that, we still have a problem in terms of the amount of data that we need to train these things. So I think there's still more work to be done, but please go and talk to Moritz. So very, very briefly, the last thing I want to talk about is the fact that I haven't really talked at all about this top layer in terms of actually getting these smart cars, these self-driving cars, or any other agent, a robot in a factory, or if you're Adam Bree and you've got like a fleet of drones flying around, how do you actually communicate in a more intelligent manner what it is that you want out of them? One of the things that I like to point out is in this architecture, even this structured optimization architecture, it worked really well because a lot of these components were built out of data. Things like system identification is basically a very early form of machine learning. And I can highlight in green here almost every arrow and say that I knew how to actually train this system with data. But these arrows here, we actually don't really know how to train them in a way that gives us the same kinds of performance that we want. And a lot of time we end up hand engineering this relationship between a high level executive. Sonia alluded to this morning when she said, you got to make sure your tokens line up with the underlying system. And that's true, but she didn't tell us how. And I think it's still because largely it's an open question, what is the right optimization strategy for generating a symbolic representation at the top level that gives us good performance throughout the entire system. So with that, I'll stop here, say thank you very much and happy to take any questions.